that's all. I hope you get the point. Let me know if there is any point I need to consider, or I need to slow down, or I think you think I can go very little lower pace, and then I will be able to prepare it according to your condition, and I will be happy to receive any type of comment and any type of input from you, because you are the audience. You need to know what I am trying to do. You need to know what I am basically trying to deliver to you. If this message is not actually completely understandable to you, then it is difficult for me to give the message, because there is no meaning, because you are not understanding. So thank you, and stay safe and wash your hands a lot. Thank you.
ওকে, গুড মর্নিং। সো আমরা মিচেলিস-মেন্টেন ইকুয়েশনটা আমরা পড়েছি। মিচেলিস-মেন্টেন ইকুয়েশনটা যদি তোমরা দেখো, এটা V0 equal to Vmax substrate divided by substrate plus Km. So here Km is the Michaelis-Menten constant substrate concentration, and this is the substrate also substrate concentration, and this is the V maximum, that means rate maximum, and this one is the our rate. Now for Michaelis-Menten equation we already know the derivation, but if we consider that special cases of the Michaelis-Menten equation, then I say to you that there is two different type of condition. One where Km is equal to substrate concentration, or Km is very less than substrate concentration. Two different condition we are considering here. If we say this is condition 1 and this is condition 2, now if we think that Km equal to substrate concentration, that means the Michaelis-Menten constant is equal to the substrate present in your reaction mixture. Now then what will happen to this equation? So V0 equal to Vmax into substrate concentration will be remain substrate concentration. I am writing only S, and here S, I said Km equal to S, so I can write S here. So from this one I can write Vmax into S plus S, 2S, S divided by 2S. Now if we remove these two, the same thing, then the final projection will be V0 equal to Vmax into half, or Vmax divided by 2. So that means if Km equal to S, then our final expression is V0 equal to half Vmax by Vmax by 2. That means when Michaelis-Menten constant is equal to substrate concentration, then the rate of any enzyme catalysis reaction will be half of its maximum rate. So this is one of the condition, that rate is equal to half of maximum rate. Now if we consider about the second condition, now for the second condition we just keep it. Okay, for the second condition, here you can see, for the second condition Km is very smaller than S. Now when Km is very smaller than S, then what will happen? Then like if you have 5,000 taka, suppose 5,000 taka, okay, you are just adding 0.005 taka with that. So is there any significant change in this addition? This is not. That means So 5000 taka plus 0.005 taka, it do not have any kind of significant value addition. So if km is very very smaller than s, then we can say that basically we can omit the value of km from this equation. There is no impact of km, so we can say this there will be nothing, because it is very negligible amount compared to this one. Okay, now what will happen? So if there is the same type of variable here, then we can say v0 equal to vmax. That means if km, Michaelis-Menten constant, is very very less than s, then the value of km can be omitted, and because of that we can say v0 equal to vmax into substrate concentration divided by substrate concentration. As this is almost nothing, then we can say v0 equal to vmax. So these are the two special conditions for each and every enzyme catalyzed reaction who follow the Michaelis-Menten equation. Now we will go to any another format that so v0 equal to vmax. Now if we consider, if you want to linearize the Michaelis-Menten equation, if you want to linearize the Michaelis-Menten equation, why we need to linearize? Because you know we use the Michaelis-Menten constant to create any type of, or to observe the reaction rate of any type of enzyme catalysis reaction. Now when we are trying to do that, so if we think about this equation and we try to draw a graph of this equation, okay, this is the our graph, then it will be basically like that, either logarithmic or like a logarithmic plot. Okay, like a logarithmic plot. So basically we the physical chemist, or the with the physical chemist, we are trying to get a linear relationship. Why? Because to get any information from this type of graph, it is difficult. But if we are able to make this graph into like this type of a straight line, then it is easier to find out any information related to this one. Okay, so now there is one of the tendency is to convert this equation to any straight line equation. Now when if it is a straight line equation, then what will happen? We know that the straight line equation y equal to mx plus c. So this one. So when it is in this type of format, then it is easier to get any information from this equation rather than the format of this one. Now if we have this type of straight line equation, then we will be able to put some value and directly can derive this one from this plot. And for this reason we go for the Lineweaver-Burk plot, Lineweaver-Burk plot of this Michaelis-Menten equation. Now to go for the Lineweaver-Burk plot, at first we need to make the equation from this type of arrangement to y equal to mx plus c. Now how to do that? If we look, so we already said that we one of the our main goal is to convert it into linear equation. Now if we consider that the Lineweaver-Burk plot, okay, now we have this one. For simplicity we can write that like that. For simplicity we can write s divided by s plus km Okay, so for simplicity we can write this one s plus km. এখন now what will happen, we need to make it linear. For linearization, what we can do, just first of all we just send this part to this side and this side to this side. Okay, just exchanging the both of the side, then there will be 1 by s divided by s plus km equal to v max divided by, sorry, v max divided by v0. Okay, now just we can make it, just simplifying this one, we will get s plus km divided by s equal to v max by v0. Okay, now if we divide both the side, if we divide both the side by vmax, divide both the side of this equation by vmax, then what will happen, then we will get s plus km divided by s into vmax equal to 1 by v0, because this vmax and there will be another vmax, it will be gone, so 1 by v0. Okay, now if we just divide these two, then what will happen, just splitting up this, then we will get, then we can say that 1 by v0 equal to, splitting up this one, s divided by s into vmax plus km divided by s into vmax. Okay, now I just run out of the board. Now the final expression from here, you see this s and s, it could be nullified, so this and this is, and there will be this one, then the final expression will be the Lineweaver, for the Lineweaver-Burk plot, the final expression 1 by v0 equal to, s and s gone, so you have 1 by vmax plus you have km divided by s vmax. Okay, we can also remove this one, so this is the expression from this one, we can go there. Okay, I think there is no problem, you can understand, just s and s gone, then km by vx, km by vmax, s vmax, 1 by v0, everything is same. Now just to rearrange to make it ideal, we can write 1 by v0 equal to km by vmax into 1 by s plus 1 by vmax. Just I keep everything same, just a little bit differently I write it, just differently. Okay, this is the same thing what written here, and this is the same thing what written here. Now why I do that? Because now you look at this. If I say this is the y, this will be the m, this is the x, and this is the c. So what will be the equation? Y equal to mx plus c. So as I said before starting the class, that we are trying to get a linear equation. We are trying to get a linear equation from this expression, and we are now obtain a linear equation from Michaelis-Menten equation. Okay. So if you look at the Michaelis-Menten equation, Michaelis-Menten equation, from this one, this is basically a logarithmic plot, but the expression which we obtained just now, it has y equal to mx plus c. So basically the straight line equation, the standard equation for the straight line. So as a result, we will be able to determine any kind of parameter from this equation easily than this one. So because of that, we go for the Lineweaver-Burk plot. Now why do we need it? Now for inhibitor preparation or any type of preparation of some like different type of enzyme inhibitor or enzymes, we need to think about that whether this enzyme is working or not, whether this inhibitor is working or not. If you want to look at this criteria, then you must have to determine whether this inhibitor is working. Suppose I prepared some inhibitor or matrix metalloproteinase. Now how could I say that this is working? Now what will I do? I will take some substrate of the matrix metalloproteinase, and then I will allow them to go for the reaction, and then I measure the this profile of this proteinase, of this enzyme, and then I will add my inhibitor to the solution, again observe this information from that equation, and when I got some result, then I will say that there is a far difference between the with inhibitor and without inhibitor. Now when you have with inhibitor data and without inhibitor data, then you will easily show mathematically that whether your inhibitor is working or it is not working. I think it is clear. Now what is this? This is the V0, the rate at any time, and Vmax, this is the maximum rate could be attained for your enzyme catalysis reaction. Michaelis-Menten constant, substrate concentration, again Vmax. Now you have different parameters according to system of linear equation. I don't know whether about your mathematical background, but we did some mathematics in our undergrad. So now if we say system of linear equation, you can look at it in any other mathematician. I am not a mathematician, but I can give you a hint. Okay, system of linear equation, according to system of linear equation, it is in linear algebra. If you want to look at linear algebra, now in according to the system of linear equation, if you have four different variable in your equation, then you must know other three to obtain one. Okay, if you have three variable, then you must know two to get one from using that equation. Now if we consider that we have 1 2 3 4 5 things here, and some of them are constant, this one is constant, sometimes this one is constant. Now if there is two constant, we have only two variable, 1 and 2. Now if we know this one, we can find out this one. If we know this one, then we can find out this one. Now how we can know the substrate concentration? Because now okay, I will discuss it after plotting the equation. Now what will be the your Now I just want to keep this one here. Okay, okay, I'm removing all of them. Okay, for time being, uh, for time being. So that means we have 1 by v0 equal to km by vmax into 1 by s, okay, plus 1 by vmax. This was our equation. Now if we plot this equation, if this is our x and y axis, and where we can put 1 by v in this direction and 1 by s in this direction. Okay, so if we plot 1 by v against 1 by s, then according to this equation we will get a plot like that. Okay, now from this plot what we will obtain? We know the c, that means this is the c. In case of y equal to mx plus c equation, this c basically determines the amount which is cut from the y axis by your graph. That means this line, the size of the cut will be this one, or that means this is will be 1 by vmax, this part, and this is common, we know all from the equation of a straight line, that this is 1 by vmax. That means from this one we can get 1 by vmax again. Now what is the km by vmax? It is nothing but m is the slope, we know this is just a slope. Okay, this is a slope. That means the slope of this straight line will be our m equal to km by vmax. Now we know 1 by vmax is this one, we know m equal to km by vmax. Now from these two relationship we can easily find out the value of the km. So from this plot we find out already vmax, we find out already km. Now we have both the value of all of them from this just a plot. We are able to determine all of them. Okay, and also the part which is basically cut from the x axis, that means, oh, I am not good at bracketing, okay, like that. Okay, so this part also give you another information, that 1 by km minus 1 by km. So however, the basically what is our concern? Our concern is that I will give you the substrate and you will know the rate of the reaction. How? Suppose I give you some substrate and enzyme, you give it, we usually use a machine which is called plate reader. Okay, you know, I think if you are from outside then you know the plate reader. Maybe Bangladeshi student is difficult for them to know the plate reader. Plate reader is nothing, it is just a spectroscopic machine which has the ability to obtain the reading of the change of the optical of the color of any solution. Now you add all of the enzyme and substrate and then push it into the plate reader, and then it will give you automatically the answer that your reaction is proceeding or not, because we add some dye into the reaction mixture which has the ability to combine with the product. Now, if reaction proceed, if your enzyme is working, then when the enzyme working, you have some product, then this product basically help you to obtain the color of the equation solution. Now, if you have the color of the solution, then this color can be measured by the colorimetric method, and this colorimetric method will say that your enzyme is basically working on the substrate in that way. Now, if it is able to work on the substrate in that way, then you will get the time required to conversion of the substrate, and from this one we can determine the rate. Again, we know what is the concentration of enzyme I am using in that solution. Is it is 5 molar, it is 0.5 molar, it is 0.005 molar or something. We can determine. So from this one you can determine the S. Now, if we know the S, if we know the V, we can plot this equation. We can easily plot this type of plot, and from this plot we can easily determine the maximum rate for that reaction, the Km value for that reaction, enzyme catalysis reaction. Now, this is the common case of the enzyme catalysis too. Just study the enzyme catalysis. Now, what will happen if there is inhibitor? If there is inhibitor, then the value of Km, Vmax, everything will be changed. Okay, so from the non-inhibition condition, for the non-inhibition condition, in the absence of inhibitor, you will obtain this thing, but in the presence of inhibitor you will obtain the different case. Okay, so there is another expression. If we look at, if there is in presence of inhibitor or in absence of inhibitor, যদি আমরা দেখি, there is a different equation, different the 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 shape of this line will be just different. From this one we can say that our inhibitor is working or our inhibitor is not working. And also from the equation, from this equation we can easily determine all the constant by using just two parameter. But from this one it was difficult due to its nature of curvature. This was like that. Okay, so now you are satisfied that Lineweaver-Burk plot give us some independence to determine the Km value and the Vmax value with a considerable confidence rather than previous one. As a result, we need Lineweaver-Burk plot from Michaelis-Menten equation, and this is just this one, just conversion of this equation to this equation in the format of y equal to mx plus c. Now, let me show you then what will happen. Okay, how we can determine the inhibition criteria of type of inhibition from Lineweaver-Burk plot. So you see, this is 1 by V and this is 1 by S. Okay, now this is the Lineweaver-Burk plot for normal case. Okay, no inhibitor. Now, if there is a competitive inhibitor, I already told you about the competitive inhibitor. So the inhibitor which has the same structure, same size of its substrate, and which can bind onto the active site of the enzyme is known as competitive inhibitor. Now, if it is a competitive inhibitor, then the equation will be like that. Then the plot what we will obtain, it will be like that. This is competitive inhibition. Okay, now if it is non-competitive inhibition, then it will be like, okay, if it is non-competitive inhibition, then it will be like that. Okay, that means the broadening. Okay, non-competitive. So I can use another color for this one. It will be easier for you to understand. Okay, don't bother about the lines. I am not good at lining. Okay, okay, this is the non-competitive inhibition. Okay, so from this one we also can show, so this is the normal case. If it is competitive inhibition, then it will be little bit striped, the slope will be high because the substrate and enzyme has the same condition to react. And if it is non-competitive, then it will be little bit more lower slope, okay, like that. This is that. So this is the basically our Lineweaver-Burk plot, and this is the, I just described two different condition of our Michaelis-Menten equation. And for one condition, it is basically, for one condition we have, the two condition was S is very greater than Km and S is equal to Km. So for S is equal to Km, we find out that V equal to half Vmax. For S is very greater than Km, we find out that V0 equal to Vmax. And for Lineweaver-Burk plot, we show you how to obtain the Lineweaver-Burk plot and what is the use of Lineweaver-Burk plot, how it could be used in our daily life or in our enzyme catalysis reaction, in study of the enzyme catalysis, and how we can use this enzyme catalysis reactions or this enzyme inhibitors, how can we study the enzyme inhibitors, enzyme catalysis reaction by using this Lineweaver-Burk plot, okay? And what is the advantage of the Lineweaver-Burk plot over the Michaelis-Menten equation? Though it is a product of Michaelis-Menten equation, but it has some advantage, okay? So this is all today. Hope you are obtain the problem and you get all of the equation I am trying to say here, and you obtain it. And also, if you have any problem, Grace, feel free to contact with me. You know my information. Okay, thank you. Have a good day. So this is Lineweaver-Burk plot. This is Michaelis-Menten, and these are two condition. And for this condition, for this one, we will get V0 equal to Vmax, and for this one, we will get V0 equal to half Vmax. That's it. Okay. The total lesson is here. Okay. Thank you.